Hello everyone. So in this video we're going to look at how we go about calculating the sine function on the Nintendo 64. There are two different algorithms that we'll go over, which use different data types for their input and output. The first will be using floating point numbers, and the second will be using fixed point numbers. Before we go into the algorithms themselves, let's take a moment just to analyse how these number formats work and how we can represent real numbers using binary. As a quick note, I'm assuming that you'll already know how to read binary numbers before continuing in this section. If that's not the case, you may want to quickly revise number bases or simply skip ahead in the video. First, let's look at fixed point numbers. A fixed point number is essentially stored as an integer but with an implied point. In base 10, we call this a decimal point, but as we're working in binary, it's referred to as the binary point. Let's say we have a number 4 binary digits long, with 2 digits either side of the binary point. The digits to the left of the point will represent positive powers of 2, while the digits to the right are negative powers. This would be referred to as a Q2.2 format number. Later in the video, we'll be dealing with numbers in Q0.16 format, meaning that all of the bits are following the binary point, so the number being represented would be between 0 and 1. A floating point number, or float for short, is essentially the binary version of scientific notation. In base 10, we often express small or large numbers by writing a decimal value multiplied by 10 raised to some power. Replace the 10 with a 2 and we have ourselves a float. But how do we express this using only binary digits? Well, let's think about it for a moment. There are 3 pieces of information that we need to store to represent such a number. These are the sign of the number, so whether it's positive or negative, the fractional part of the multiplication, and finally the exponent, which is the power that's being raised to. We can store the sign in a single digit, 0 for positive and 1 for negative. The exponent is always going to be an integer, so we represent this as a string of 8 bits. To allow for negative values in the exponent, the integer being stored will have 127 subtracted from it, giving us a range of 128 down to minus 127. The remaining 23 bits will represent the fractional part, which is also known as the mantissa. As you might have guessed, this is handled the same way as a fixed point number. While there are only 23 bits stored, there is an implicit leading bit which is always set, meaning that the number being represented will be in Q1.23 format and will have a value between 1 and 2. With a total of 32 bits, this is what we refer to as a single precision floating point number. There is also a double precision format, which increases the number of bits used for the exponent and mantissa and represents, yep, you guessed it, more precise values than the single precision format is capable of. While this is an overview of how floating point numbers work, I haven't gone into the full details regarding any special values or exceptions to this format, as it's really beyond the scope of this video. If you are interested, I would encourage you to go and read up more about the formats. With these in mind, let's now see how rotations can be stored using these formats. Everyone will be familiar with degrees, where 360 degrees represents one full rotation. If you have studied mathematics, then you'll also be familiar with radians. In this case, one rotation is represented by 2 pi radians, and when we're using floating point numbers, it will be radians that are being used. So what about fixed points? Well, we cannot easily scale our fixed point number to either of these systems, which leaves us with a problem. What is the best way to represent an angle? Well, I'm glad you asked. In fact, we will introduce a third way to measure angles using the full range of our fixed point number. We call this system binary radians, or tones if you would prefer a slightly more boring term. In this system, we store a fractional number between 0 and 1 representing the number of rotations. On the Nintendo 64, it's very common to store this in a 16-bit number, which is where the Q0.16 format that I mentioned earlier becomes relevant. So now that we've had an introduction to the number formats involved and how to store angles, let's look at how we can actually calculate the sine function. First, we'll be looking at the floating point version. In this case, we calculate sine using the Taylor series. The Taylor series is a method of approximating a function using polynomials of increasing degree. To get an idea of what this means, here is a graph of the Taylor series approximations to sine up to the 9th degree. The degree in this context just refers to the highest power of x appearing in the equation. We can see that the 9th degree polynomial is a decent match for sine between minus pi and pi, which is one full period. It shouldn't be surprising then that this is the polynomial we'll be using for the calculation. But that's not quite everything, as the function has to be prepared for input outside of this range as well. So what happens if the angle is large? Well, for any angle greater than 2 radians, we instead calculate the result based on the distance from the input to its nearest multiple of pi. In the equation shown, the square brackets are used to denote rounding to the nearest integer. As this maps all inputs to a range of minus pi over 2 to pi over 2, we need to keep track of whether the factor of pi that we calculated was odd or even. For odd factors, the result then needs to change sign, as the remapped value will be in antiphase with the original value. What's also worth noting is that for small inputs, less than 2 to the power of minus 12, the function will simply return the input value. This is known as the small angle approximation, which is commonly applied in fields such as physics and engineering. This simply stems from the fact that the closer we get to 0, the closer the sine curve can be approximated by the line y equals x, or in other words, the value of the sine of the angle approaches the angle itself. While this function takes a single precision float as input and outputs this type as well, all of the steps in the calculation itself are performed in double precision to minimize any rounding error introduced by the limited precision of these data types. In fact, there are even 2 double precision floats used to represent pi to as many decimal places as possible. While this may seem unnecessary, there can be a significant error introduced if the function takes a very large value as input, and the extra precision works to correct for this error. The fixed point version of the function uses a different method. This time, we pull the result from a lookup table. That is, the game will store a list of pre-calculated values describing one quadrant of the sine function, namely from 0 to pi over 2. The other quadrants can then be determined from this via reflection around the x or y axes as appropriate. So how do we find the correct value from this table based on the input? Well, we need to take a look at our angle in binary. First, we shift this number right by 4 bits, giving us 12 bits left to work with. We then split this into 2 numbers. The lower 10 bits will be our index into the lookup table, and the upper 2 bits tell us which quadrant of the function we're looking at. For a quadrant of 0 or 2, we index from the start of the table, but for quadrants 1 or 3, we index from the end of the table, reading backwards, as the curve has been reflected horizontally. For quadrants 2 and 3, we also need to make the result a negative value, as we have reflected the curve vertically. So, because we shifted our bits to the right, we will have multiple inputs mapping to the same values, meaning that the result will be a step function. Specifically, for each quadrant, we will have 16 input angles mapping to each output, with a total of 1024 possible outputs. These values are stored in 16-bit fixed point numbers, which are actually normalized to a value of plus or minus 1 when their integer equivalent is plus or minus 32,767. Due to the fact this table needs to contain both the minimum and maximum value for each quadrant, those being 0 and 1, the period of the function is slightly compressed to ensure that the peak is reached at the final table entry, one data point before the true peak should occur. Now let's say we want to determine an equation we can use to generate the lookup table ourselves. We already have the conditions that the function crosses the origin and has a peak of 32,767 in its integer representation. We also know that we must truncate any fractional parts of numbers we calculate, as we will need to store results in only 16 bits per entry. We can then use these conditions to describe a sine wave, and plugging in all values of x between 0 and 1023, we can recover the exact lookup table that is in use. So after looking into both of these functions, what's really the difference? Well, the floating point calculation offers a more precise result than the fixed point, but it requires more processing time. In games such as the Zelda games, rotation is commonly stored as a fixed point number, and it's accurate enough to use the fixed point version of sine and cosine for any calculations based on this. An example we can use is how actors update their velocity. An actor will store its total speed in a single floating point number, but to apply this to updating the actor's position, we need to store it as a vector so that each component of the vector can be added to the actor's coordinates. The actor's rotation around the y-axis gives the direction it's facing, which will also be the direction for it to move in, so by plugging this rotation into sine and cosine, we can easily calculate the components of this velocity vector. In games that rely more heavily on mathematics, such as Mario Golf, it's more appropriate to convert angles into radians and use the more precise method to calculate sine to try and retain as much accuracy as possible in the calculations. So in this video, we've had a brief look into number formats and how to calculate the sine function on Nintendo 64. As always, I hope you learned something from this video, and thank you for watching.